Now, so let's look at some more examples, right, to get some more clarity on what the symbolic strongest post condition does. Right. So now let's try to again calculate, right, what will be the strongest post condition for this particular problem, right. So y is greater than 0. So this is a set of program states. This is my f, and my statement is x equal to havoc, right. So again I want to kind of express all possible program states that are reachable after executing x equal to havoc on a state where y is greater than 0, right. So I know that x equal to havoc will assign any value, right, to the variable x, but the value of the variable y will not be affected, right. So what I expect is that the value of y should continue to remain greater than 0, but I cannot say anything about the value of x. Okay. So let's try to derive this again from the definition, right. So from the definition, right, which is, so if you recall the definition, right, so we say SPFC is defined to be there exists V such that f and rho c, right, where after this you do the quantifier elimination followed by the substitution. So let's just apply the definition. So here SP of y is greater than 0 and x colon equal to havoc. This is going to be there exists V, so there are two variables x and y, so there exists x, there exists y, f, right, which is y is greater than 0, and rho c. So rho c here is the encoding, right, of havoc statement. So again if you recall, right, the encoding of havoc statement was what we call frame x, right. So what we essentially say is that the value of the unprimed version is the same as the value of the primed version for every variable except x, right. So this in this case will mean y prime is equal to y, and the value of x, the value of x prime is unconstrained, right, which means that x prime, the primed version of x, right, which is the value of x after executing the havoc statement, it can take any value, right. So now this is the formula that I get, right, this I get directly from the definition, okay. And now I need to do quantifier elimination. So I need to eliminate x, I need to eliminate y. Now here things are quite straightforward. I can just directly remove this there exists x because there is no dependence on x. I can also directly remove there exists y, right, except that this I have this y prime is equal to y, but then I know y is greater than 0, so therefore y prime will also be greater than 0, right. So this is equivalent to y prime greater than 0, right. And after I do this I will do a simple substitution, right. So I will replace the primed version with the unprimed version, so I get y greater than 0, right? So this is the final formula. So y is greater than 0, right, and again intuitively it matches, right, what it is that we expect, right, because if you do x equal to havoc, all you can say is that if y is greater than 0, y will continue to remain greater than 0, but you cannot say anything about x. So in general, right, I mean if you have some arbitrary formula f, then the strongest post condition of this formula f with respect to x equal to havoc is simply this formula there exists x dot f. So if you again look at this formula carefully, right, there exists x dot f. In this formula x is not free, right. So when we say x is not free, that means that x itself, right, can take any value. So this formula, it does not constrain x. Because x is no longer free, right. So if you take any value, right, any model of this formula, it will not constrain the value of x, right, but it will constrain all the other program variables. Okay, so let's look at the assume statement now, right. So again, what will be the strongest post condition of f and assume g? So again, intuitively, what does this mean? So we have a set of program states which are encoded by the formula f. Now on this like giant set of program states, I want to execute this assume g statement, right. So I know that assume g, what is it going to do? So it's going to filter out all those program states which satisfy f, right. So assume g, right, will only allow those program states to proceed ahead which satisfy the formula g, okay. Now what will be the final form of this SP? So again we will derive this from the definition, okay. So SP f assume g, this is what we want to derive, okay. So I use the definition. So the definition says this is defined to be there exists V, f and rho of assume g, okay. So there exists V, f and rho of assume g. So rho of assume g again you have already seen earlier, right. So this particular the encoding of assume g, right, was defined to be G and frame phi. What this means is that this encodes all program states, right, where the unprimed versions should satisfy G and the primed versions should be equal to the unprimed versions. Right? That's what frame phi means. Right? So frame phi means that for all variables V, the primed version is equal to the unprimed version. Right? So I just use that particular definition. Right? So this is equivalent to there exists V, F and G and frame phi. Okay. Where frame phi is simply so if I expand on frame phi, right, so this is simply V prime is equal to V. That's all it says, right? That for every variable its primed version is equal to the unprimed version. Okay. So now in this formula again I want to eliminate, right? So I want to eliminate all the existentials, right? So I want to eliminate all the unprimed versions, right? So how do I eliminate? So again if you squint at this very carefully, right, so you can see that I am saying that V prime is equal to V, right, but all of my unprimed versions they satisfy F and G. So this will encode exactly those set of states where F and G are satisfied, right, but F where V prime replaces V and G where V prime replaces V. So if you look at this formula, right, this formula, it doesn't contain this existential on V, it only contains the primed versions, right, as free variables. So I obtained this formula by essentially taking the formula F, taking the formula G and replacing every unprimed version with the primed version. And this I can do because the values of the unprimed version are simply equal to the values of the primed version, right. So therefore this is the formula that I get, and now I do another substitution, right. So in this formula all my free variables are the primed versions. So again I will again replace back the unprimed versions for the primed versions, right. So in this formula I will do V replaces V prime. So this is like doing the same substitution, right. So first I substituted every unprimed with prime, and now I need to substitute every primed with unprimed. So I will again get back the same formula, right, which is F and G. So this is the final result, right. So this is what you will get, which is F and G. And again intuitively, right, let's think about for a moment, right, intuitively does it make sense, right. So what are all the program states that I can get after executing assume G on the set of states which satisfy F, right. So I know that my input set of states, right, they all satisfy the formula F, right. Now if I filter them through assume G, my output set of states will have to satisfy G, and in addition of course they will also have to satisfy F, right, because all of my input states satisfy F, and assume G itself doesn't change any of the program states, right. So it only filters through those states which satisfies G, right. So that's why the final set of program states, right, that you will get after executing assume G will satisfy both F and G. Okay. So let's do one more which is assert G, right. So let's try to figure out what will be the strongest post condition of F and assert G. So again, right, we will go step by step. So we will use a definition and we will try to see where it takes us, right. So SP of F and assert G. So this is defined to be there exists V, F and rho of assert G. Which is there exists V, F and so rho of assert G we had defined earlier, right. So this was defined to be G implies frame phi, right, which essentially means that either G is satisfied, either G is not satisfied, right, in which case the unprimed versions are free, right, so they can take any value, they are unconstrained. So sorry, if G is if G is not satisfied, then the primed versions are free. If G is satisfied, then the primed versions are equal to the unprimed versions. Okay. So let's try to simplify this. So you'll get there exists V, F and so this is not of G or frame phi. So now I am going to use distributivity, right. So I know that AND distributes over OR. right. So I am going to have there exists V F and not G, or F and frame phi. Okay. Now I am going to use another form of distributivity, which is that the existential quantifier, it distributes over disjunction, right. So this is something that again you should try to figure out, right. So if you have a formula like there exists X, Px or Qx, right, then this existential quantifier can be distributed over the disjunction, right. So I can write this as there exists X Px or there exists X Qx. So this is not true, for example, for conjunction, right. So the existential does not distribute over conjunction, but it does distribute over disjunction, right. So if I'm going to distribute this existential over the disjunctions, I will get there exists V F and not G, or there exists V F and frame phi, where this frame phi is simply saying that V prime is equal to V. Now here I want to again do elimination, right. So I want to eliminate the existential, right. So in particular, right, if I look at this particular formula, right, there exists V F and frame phi. So frame phi is simply saying that the primed version is equal to the unprimed version. If I eliminate the unprimed version, right, again through the same kind of procedure that we saw when we derived this assume G, right. So this thing, right, this is going to become F where V prime replaces V, right, because V prime is equal to V, right. So this formula, right, it describes all those primed variables which are equal to the unprimed variables, and the unprimed variables satisfy F, which is the same as saying that all the primed variables satisfy F, right, because the primed variables are equal to the unprimed variables. So if this, so this will be F where V prime replaces V, and then you will again do another substitution, right, where V replaces V prime, right. So this whole thing is going to simplify only to F, or there exists V F and not G. Okay. So this is the final formula that I will get, right, which is there exists V F and not G or F. Now again let us take a minute, right, and try to kind of understand, right, what is this formula really saying, right. So think about all models of this formula, right. So what it is saying is that so there is a disjunction here, right. Now if there exists a V such that F and not G, F is the set of input states, right, not G are those states which are going to violate the assertion. So if there exists an input state which violates the assertion, then there are no constraints on the primed variables, right, there are no constraints at all, right. So when I say there exists V, right, this part of the formula, it has no free variables. So it has no free variables means that it does not constrain any program variable at all, right. So no program variable is constrained by this part of the formula. This part of the formula does constrain program variables, right. So it says that the program variables should satisfy the formula F. So if the assertion is violated, right, which means there exists some program state which satisfies F, but it does not satisfy G, then there are no constraints on the program variables at all, right, which means that any program state is reachable, which means that the error state is also reachable, which is exactly what we want to encode, right. Or if it is not the case, right, so if there does not exist a V such that F and not G holds, right, then all of my program variables, they are constrained by the formula F, right, which is just the input set of states, right. So again if the assertion passes, right, which means that all states in F satisfy G, right, then my output set of states are all going to also satisfy F, right, because that is what my input set of states is. So the assert simply allows all states which satisfy F to flow through, right, without making any changes, right. So that is how intuitively, right, this formula it encodes the semantics, right, of assert G, and we also derived this formula from the definition. Okay. Okay. So I am going to end here and we will continue in the next lecture, right. So we will look at some examples of assumes and asserts, right, and we will also look at compound program statements and define strongest post condition for these statements. Okay, thank you.